stratification at a variable, right? Y is equal to 1, 2, or no more than m. So you have to make sure this stratification variable is finite. Otherwise, how do you allocate your simulation budget? Okay, let's see how it's defined. Y equals 1 if n equals 1, with the corresponding probability P1 equals P, right? Because n is a geometric random variable, P1 is just P. Success is done after one coin tossing. Y equals 2 if n equals 2 with probability P2, and y equals m minus 1 if n equals m minus 1 with probability P sub m minus 1, which is equal to, I think this is a typo here. It should be the probability n equals m minus 1, not 1. n minus 1 here. Right? This is n minus 1. And the corresponding probability would be n minus 2 failures times 1 success. Okay. The final one, you have to learn to stop, right? You can't do infinite cases. So y equals m if n is greater than or equal to m. With the probability Pm, that is equal to the probability n is greater than or equal to m, meaning you fail m minus 1 times, and you don't know when you're going to stop. So, the termination is after m minus 1. Can be m plus 1, and so on. So in that way, you define a y which has a finite support from 1 to m. You can stratify on y. For example, let's say m equals 3, and you do the PSS, proportional stratified sampling. Right? Let's say if y equals 1, generate n1, right? n1 is given by this. n1 the copies of the indicator. Given y equals 1, L equals just V1, right? So, because, L is a summation of y, and y equals 1. So there's one, y equals 1 means n equals 1. So L is equal to 1 of the V. It's 1 V, 1 accident only. So, right? So, generate the V and check whether or not V is greater than L, and if yes, return 1, otherwise return 0. Do this n1 times and return the sample mean. Because n1 is your simulation budget here for this case. If y equals 2, generate n2 copies according to this formula. n2 copies of indicator of L given y equals 2. When y equals 2, L is equal to V1 plus V2. So you have 2 accidents. And generate 2 V. And check whether the sum of the 2V, 2 accident claims, greater than L. Okay, no problem. Compute its sample mean. When y equals 3, here 3 is our m. Note that there's a lack of memory property of n, implies that n given n greater than 2 is n plus 2. What do I mean by that? N is a geometric random variable. If you know you failed 2 times, does this say anything about how many extra steps it takes until you have a success? No, right? So n given n greater than 2 is equal in distribution to n plus 2. So in this case, you know how many n, you know how many claims to generate. You generate a geometric random variable having probability p, and you just say, oh, I'm going to do n prime plus 2, because this is the case where I'm going to have n plus 2 many claims. That is the conditional distribution of a geometry given the geometry is greater than 2. Okay? So, what am I doing here? 3a is to figure out how to simulate the number of claims in the third case. This is different from the others. The others tells you exactly how many claims you have. You have 1 or 2. Here's not 3. Here's at least 3. So it's going to be 2 plus a brand new geometric. Okay? So your n would be n prime plus 2, where n prime is geometric. Depending on whatever n you see from 3a, you're going to generate the ni copies of v and return indicator summation of v greater than L. You see, if the summation is greater than L, you return 1, otherwise you return 0. Repeat n 3 times and obtain its sample mean, and aggregate the sample mean using P as weight. This is your stratified sampling estimator. Okay. So this example teaches us how to stratify on a random variable that has infinite support. You have to learn when to truncate, right? So couple of remarks. So first, we have partially eliminated randomness in n to reduce the overall variance. Have we eliminated all the variance in n? We haven't. We still have to generate n in case 3. Case 1, we did not generate n. We just say n equals 1. Case 2, we did not generate n. We say n equals 2. Right? So come back here and look at the crude Monte Carlo estimator. The variance comes from two sources. There's randomness in the generation of n. Given n, there's randomness in the generation of vi. The goal, the idea of stratified sampling estimator is to eliminate randomness in n. But we can only do so partially. Here, in case 1, we don't have to generate n. We know n is 1. In case 2, we don't have to generate n. We know n is 2. In case 3, we have to generate n. We have to generate a random variable that is geometrically distributed and add 1. Right? So we have partially eliminated the randomness in n. We cannot completely eliminate randomness in n because n is infinite support. Right? We also take into account the case of large losses. See what I mean by that? Take a look at this crude Monte Carlo estimator. Right? Suppose this L is really big. So let's say the probability is very small. Let's say this probability is very small. Let's say the probability is 10 to the minus 6. Then on average, you will have to generate 10 to the 6 many samples to get 1. Right? You're generating ni, the copies of the indicator. If the probability is very small, as small as 10 to the minus 6, then that means when n is equal to 10 to the 6, you should have about 1. The others are all 0, right? Okay? So this worst case never happens actually. It never happens. So your variance would be very big. And it's very crude. But here, case 3. We put ourselves in a position where we are pretending we have a large number of claims. So case 3 enables us to more likely obtain a 1. See, if L is very big, if L is big, case 3, you are more likely to have a 1 returned because you pretend that you have 3 claims. Right? So you take into account the case of a large loss. You intentionally generate the case you have a big n. Because case 3, I'm generating this thing. I'm generating 3 or more copies. So it's more likely for me to have a 1 than the other 2 cases. Of course, the probability of this case would be smaller because the probability is really getting smaller and smaller as n increases, right? So we are taking into account the case of large losses. We are able to generate the large losses. But in this example, we're sort of unable to generate, the large loss case because in general, we don't see a large loss. This is another feature of a rare event simulation. When the event is very rare, then it's difficult to get an accurate estimation of it unless you have extremely large number of simulation. Unless you have a small and very, very large, right? So it's inefficient. I have a homework problem on this, so you can sort of check. You can sort of conduct crude Monte Carlo simulation and stratified sampling estimation and compare the variance. You will see, right? You will see this one has a much smaller variance. Okay. Final example here is related to option pricing. Consider a European option and the stock price evolves according to this geometric Brownian motion. Recall that the European call option, the price C0 is equal to this formula, right? So we're aiming at estimating the expectation of this random variable here. This random variable we call it x, and x is some kind of function h of z, right? So this is x is h of z. Where is z? Z is this, right? So this geometric random variable, geometric Brownian motion, st is equal to s0 exponential drift volatility, and there's a z. Okay. We hope to estimate the mean of x. Using continuous stratification, so we stratify on z, and z is continuous. What do? We cut the entire real line into a finite number of intervals. See, we consider stratum intervals of the real line. We consider k intervals. For instance, A1, the left end point is minus infinity, and BK, the right end point of the last interval, is plus infinity. It's okay. All right. So we have some intervals that has infinite length. So we can partition the entire real line into k, a finite number of intervals. The probability that z falls into the corresponding interval is equal to phi of bi minus phi of ai, right? Okay. So we know the p, right? Pi is equal to this. All we need to do is to generate the NII, the copies of H. So NI, you can allocate the NI according to PSS, or you can do better by optimizing NI star. So generating NI, the copies of HXI, and XI is the conditional distribution, given that I think I made a mistake here. This is Z here, because we're stratifying over Z, and this should be estimation of X given Z falls into the right interval. Right? So X given Z falls into the interval, because this is the case of Z, right? The PI. And compute the sample mean by averaging those ID copies. Okay, how do we generate this this copy? So again, there's a typo here, right? How do we generate inverse transform? How do we do inverse transform? We can do inverse transform to generate a copy of xi, which is x given z falls into the interval delta. Right? Z is in delta I. Okay. How do we do this? We do inverse transform. Right. So, normal random variable, its distribution, given that normal random variable falls into an interval, can be done by inverse transform using a random variable u that is not between 0 and 1, but between phi ai and phi bi. So, you have a normal random variable, you don't do 0, 1, you do a subset of it. So think about the inverse transform, and you flip you throw a point over the y region, the y index, the y axis, but you don't throw it between 0 and 1, you throw it in the sub area. So after the map of the inverse function is gonna be between a and b, right? So think about why we have a phi of ai and a phi of bi, because if you do the forward transformation, that's how the interval got mapped, right? The interval ab is mapped into phi a and phi b, because both of the numbers are between 0 and 1. Okay? So the stratified sampling estimator would be this, right? The PI is known, and we have a technique to estimate xi, right? Okay. So this is example 4. This wraps up the stratified sampling estimator. That's good for today. Still repeat for me?